All right, so let's see. Your assignment number 2, which will be on singly linked list. So what we're going to cover today and Thursday will definitely help you on that. So it's going to be released most likely tomorrow. So once it is released, I'll talk about it briefly on Thursday, right? But you can expect it to be released tomorrow. And your assignment number 1 about solution, when you go over that, if you got any question, do let me know. And split array harder, I'll leave that for a few more days for you to try, and then I'll give you the solution for that. That's also going to help your programming test number 1. And lecture note template, I kind of show you guys, is on the lecture site. You can just download it each time before the class if that's going to be useful. And we got office hour, TA contact information, all the same. Yes?
Is the array harder solution a video or just a source code?
Would you prefer video or source code? Video, okay. I'll do that for you only. Okay. Yeah, I'll do that anyway. So yeah, I'm going to release the source code and maybe some very brief walkthrough about how you can think of it and maybe some simple tracing just to help you guys, right? Okay, let's now do some recap about last Thursday. So last Thursday, we basically just talked about selection sort, insertion sort, and let's now take a look. And then guys, pay attention to the wrap up right now because I do have some exercise for you after the wrap up, the recap. So it's more like an exam kind of format of question, which I'm going to discuss with you. So you can also think about it, and then we'll go over the solution together. But let's now do some recap about last time. So we kind of clarify about the different sorting orders. So not much to say. You just got to remember the mathematical relation for each one of them, right? So all these. So depending on which one is being asked, you got to implement your code accordingly. Of course, changing the order is not going to modify the running time, most likely. But it might change the logic of your program. So you got to watch out for that. And we try to relate different sorting order. So this is just one example. So proper subset in this case will be the most accurate way to do it. Even though subset might work, but proper subset will work even better, more accurately. So we talk about you should find at least one witness in the larger set. Somehow you can show that that witness is actually a member of the strictly larger set, but it's not a member of the strictly smaller set, right? That's really the pattern you want to get used to. If I can write into any similar occasion, we can keep revisiting this important idea, which is very practical for you to know. And we talk about selection sort and insertion sort. So the most important 2 lessons we learned from last time are not really about selection sort, insertion sort themselves. Number 1, you can already derive very accurate running time just by sketching the critical steps without even coding. Lesson number 1. Lesson number 2, even when you're given the potential implementation for each sorting, you don't necessarily have to understand the logic of the code before you derive the running time. So these are the 2 most important lessons we learned from last time, right? So that's something you really want to take and maybe practice that in different occasions. And for selection sort, again, you can maybe rewatch the lecture recording from last time. The most critical thing you want to remember is the selection process is going to dominate the sorting. That's why it's called selection sort. And we said that the very first selection is going to be the most expensive one, right? You can see the first one, selection, is going to be about selecting the minimum from the entire unsorted area. And the number of selection we have to really make correspond to how many steps in total that we have to do for the algorithm. You can think about the number of steps simply correspond to what would be the size of the sorted region that we want to build eventually. That's going to be just correspond to how large the input array is, right? That's something you want to really keep in mind when you review this sorting algorithm. Well, again, we got decreasing cost for selection from n all the way down to 1. All right, that's one thing. For insertion sort, it's kind of asymmetric. The number of steps is roughly still about how long or how large the sorted area is, which correspond to the input size. And then we said that the cost for the insertion is going to be the cheapest to start with because you only got, let's say, the sorted area start with just 1 element in there. If you want to insert into it, the worst case will be shift just entire region of size 1 to the right by 1 position. So that's going to be just cost 1. And then the very last insertion that you have to do is going to be you want to shift the entire n-1 region right? N minus 1 element all the way to the right by 1 position. That'll be the most expensive insertion you have to do. So overall, the insertions are going to be of increasing cost as opposed to decreasing cost for selection. All right, guys, any question from this? Right, that's the most important facts about these two sorting algorithms to remember. Everything else can just be derived from there. Right, and then we kind of spoke about selection sort without diving into the details for the logic. That's really the second lesson I just mentioned. Given a piece of code, you don't really have to understand the precise logic in order to derive the most accurate asymptotic upper bound. That's exactly what we did last time. And don't forget, you do have the exercise over here for the insertion sort. And then also very important, let's say now we want to understand the logic for both sorting algorithm. So this will be this has been assigned to you. You want to trace the program, and then with give an input over here, for example, and then use both the paper and Eclipse debugger. Right? So very important exercise for you to do to complete the learning. And I'll make sure I ask you something about it in the test and in the exam. All right, please study for that. Get prepared. All right, and just additional exercise for you. You can watch the recording from last time to see what exactly the exercise is. And then we did a little bit of intro about syncly linked list. I'll get there once we get there. Okay. Any question about insertion sort, selection sort in general? So here's a question for you. And this, I should really give credit to Ben, not from your section here, but from the evening session. That's the question Ben actually asked during the class last Thursday. I thought it's a very nice way to really think about asymptotic upper bounds and try to think about like a potential innovation on the algorithm, right? So that's could be one good example. All right, so now I'll give you the question precisely, and I'll let you take 1 minute to think about it, and then I'll just go over the solution directly. So you guys really take the opportunity for 1 minute to think about how would you answer that if this was on the exam, for example. So here's the context. We say that for insertion sort, the cost for the insertion are increasing. Right? The last insertion will be the most expensive one, shifting everything of size n-1 to the right by 1 position. For selection sort, symmetrically, the cost of selection will be decreasing. So the first selection, selecting the minimum for the entire unsorted area, will be the most costly. Right? So that's what we know from the recap. So now here is one idea. And you got to justify whether this idea is good or bad, or whether it's valid. The idea will be given that insertion sort are going to somehow insertion will be the cheapest in the beginning. Why don't we do insertion sort in the halfway through? And then for the second half, we're going to do selection sort. So what do I mean? Imagine that if you got this array over here, I got n element here. Initially, all the n elements are unsorted. Eventually, I want to get to the sorted array of n elements. Let's say I want to say from the sorted area being empty all the way to n divided by 2, like a halfway. Right? You can assume, let's say n is an even number, just make it a little bit easier to think about. Right? So now we want to do n divided by 2 insertions. Because we know insertions is guaranteed to be the cheapest in the beginning. 1 plus 2 plus all the way to maybe n minus 2. Sorry, n divided by 2. And starting from this point, once we have sorted about half of the array, we're going to switch the algorithm to say now, rather than doing insertion, because it's going to be more and more expensive, why don't we start doing selection? Because selection is guaranteed to somehow drop its cost all the way down to 1 when we only need to select the minimum, right, in the last step, right? So now for the second half, we're going to do n divided by 2 selections. So this is a proposal made to you. Let's say you're the engineer or scientist to judge to see whether this innovative idea by your colleague is actually valid or not. So here's the question. Is this new algorithm here doing n divided by 2 insertions followed by n divided by 2 selections going to be asymptotically more efficient than either selection sort alone or insertion sort alone? Guys, take 1 minute. Of course, the actual answer in the exam or in the test may not be just yes and no. Yes and no might be just part one. Part two, you got to give detailed justification to support your answer. Okay? If you believe it's better, you got to show it to me. If you don't believe it's better or even worse, you also got to justify. Okay? Okay, another 30 seconds. Don't feel any pressure. I'm not going to point to anybody. I'm going to go over answer with you. But at least we can do some quick hand raise about how many of you might think is actually more efficient. Just in a moment. Okay? 20 seconds. Okay, just 10 more seconds, and then I'm going to have a quick survey from you guys, and then we'll go over the answer. All right. How many of you think this new algorithm here is going to be better asymptotically? Nobody? Okay. How many of you think it's going to be worse? How many of you think it's going to be the same? Wow. Part A, good. All of you got the full marks. Okay, part A is good. All right, that's good. For part B, I'm going to go over the answer. Maybe that's what you're thinking then. I'm very proud of you guys. So let's go over the answer very quickly, justification, and then that'll be it. All right, so first of all, let's now talk about the justification. If you're going to do insertion, we know that it's going to have increasing cost. So if you think about just the insertion sort alone, okay, it's going to be 1 plus 2 plus all the way to the last insertion that we have to make, roughly about n over 2. That's going to be the dominating cost for insertions. Of course, you might be thinking, what about, let's say, once we choose the, how about choosing the leftmost element from the unsorted area? That one there is going to be dominated anyway, so that's why I'm not discussing it here. I'm only discussing the critical steps. All right, quick annotation. So think about this is the first insertion to make, the cheapest. So this will be roughly the n divided by 2 insertion. Okay, I'll get there about calculation in just a moment, but I can see that it's an arithmetic sequence. No surprise. And what about selections over here, right? So we're going to start selecting from this here. So the very first selection is going to select the minimum from n minus 2 elements in the unsorted area. Agree? Okay? That's how we grow the area. So you basically got to grow the sorted area differently in the first half versus the second half. That one there is going to be big O of. Now, the very first selection is going to be n divided by 2 plus n divided by 2 minus 1, right? Just one element smaller. And plus all the way to just 1. Right? And let's now do some very quick calculation, right? So this is the arithmetic sequence. So the beginning is 1. The end is n over 2. And then how many terms are there? N over 2, right? N over 2, and then the whole thing divided by 2. And you can see, you don't need to simplify any further. N times n, n squared. That one's going to dominate. So I can say that's big O of n squared right away. Right? In a very similar fashion, except that the common difference now is going to be minus 1 as opposed to plus 1. Right? So for that one there, you're going to have right here. So you got the very first one is going to be n over 2 plus the n term will be 1 multiplied by how many terms? N divided by 2, right? Just n divided by 2 all the way down to 1. N divided by 2 and the whole thing divided by 2. Again, you can see we got n times n. The rest will be lower terms or multiplicative constant, which can be dropped. So that's also big O of n squared. So overall, we got big O of n squared plus n squared which will be big O of n squared, right? So that's a final answer. It's not better, it's not worse, just the same. No magic, all right? But I can feel free to do that if you feel more comfortable, all right? So it's really the same. Also, does it really matter? Let's say if you do selection first as opposed to insertion first. Think about that. That's one thing. So think about different variants to this problem here. Variant number 1. What about I do n divided by 2 selection first, followed by n divided by 2 insertions. Variant number 2. Rather than having n divided by 2 over here, maybe I'll do a little bit more insertions. Maybe I would say I'm going to have until maybe n divided by, I'm going to have over here 2n divided by 3 and n divided by 3. I'm going to do 2/3 insertions followed by 1/3 selection. Is it going to make a difference? Think about it. All right. All right. Any question to this exercise? Yeah.
So maybe I'm just thinking about this wrong, but isn't it not able to work this way if we do insertion first as opposed to selection because the sorted area is relative in order?
Nope.
Like,
nope. So thinking this way. So the way you do insertion sort, selection sort is you always start with some sorted area and unsorted area, always. It's just that if you do insertion sort right from the beginning, it's just that the sorted area might just be of size 1 or even empty. Doesn't really matter. As long as you got one area that's already sorted, the other area is unsorted. You can definitely work out how to grow one and shrink the other accordingly, either use insertion or selection.
But if it's selection, don't we pick from the unsorted area, the smallest from the unsorted area? But if it was, the sorted area was from selection, it's relative in, like, within the sorted region. It's not absolute order, it's more like relative order between each other.
Yeah, I see what you mean. So that's something that will be some. I do see what you mean. Let me address this on Thursday. There'll be some special case to consider. Okay, let me get back to you. Yeah. Good question. I'll get to it. But the overall idea is really about whenever you are given some variance to the algorithm, you want to really think about asymptotically, is it really going to make a difference? Okay, think about that. And then I will talk about that one as well, okay, on Thursday. Just give you a little bit more context. All right, if no further question here, let's now move on. Okay. So let's now move on to, so we can draw a closure on the sorting algorithm for now, but we're going to cover a little bit more later. Let's now take a look. Let's say singly linked list, right? So that's going to be a very important part that's going to also be covered by your programming test number 1. So let's now talk about it. We started with some very gentle visual introduction. We'll continue with it. And then I'll try to give you also some intuitive ideas about how to implement different operations on the linked list. That's something we'll get into as well. But we also hopefully will see some code and do some tracing. Okay. All right, quick reminder for arrays. We know pretty well from all the previous lecture that arrays are very well performed for indexing, right? But it's very bad in inserting and deleting. That's something we know, right? And we're going to contrast these kind of operations with linked list. Symmetrically, somehow, in general, whatever that kind of perform badly in the array, you will perform quite cheaply or efficiently in the linked list, and vice versa. That's kind of the general principle. But we're going to see in detail, of course. All right, so that's what we were at last time. Was this, right? We'll talk about singly linked list is simply a chain of connected nodes over here. And we saw some visualization over here. So you got each node contains basically 2 references. One would be the reference to some data, and the other one would be the reference to the next node. Okay, so that's very important diagram, but we're going to see more also today. Also, aliasing over here. So which part is really the aliasing? So aliasing, of course, you can say that it's more like a reference to some string, as long as you got like a reference to some objects. It's like aliasing, right? But for now, we're more focusing on the aliasing to the node itself. All right? So now aliasing here, I'll just give you one example here. let's say in this particular chain of nodes, in order to refer to, let's say, this particular node, how many ways are there, right? At the moment, the only way for you to get there would be you can say n dot next. That's the only way. But what about we also, let's say when we first created that node, we also say that node was created with the reference, maybe, for example, n, because it's storing mark, let's say, right? Let's say we just introduce another variable. In this way, there are two ways for you to refer to this same node. You can either say n over here, or you can say n dot next. So these two will have the same reference, right? That's aliasing. You will see many occasions like that that you have to manipulate to really implement your algorithm. So here I can say, for example, we got just n, or that's simply equal to n next. Right? So these two simply refer to the same. Of course, sometimes you may have three or more expressions referring to the same objects. That's about aliasing. And then if you look at the slides, there is one term over there mentioned about connected nodes, which is by the next reference, aliasing. And we say linear sequence over here, right? Let's explain what's really linear and what's non-linear. Because once we talk about tree later, we also got to revisit. But it's a very important idea, right? So let's now move on to a new page here. So we'll talk about linear versus not linear. Collection. Both arrays and linked lists, they are so-called a linear collection. Okay? What does linear really mean? A simple definition would be that means each node or each position has a unique successor. Each position in the collection has a unique successor. Okay, so uniqueness over here is very important, right? Let's now visualize exactly what I mean by that. Let's say in the case of the array. So now if I got, for example, let's say here, this is my array, starting from index 0, and then it's going to be the case that if I got I here, the successor will be the position to its right, which will be I plus 1. There's only a single successor relatively to this I here. There's a unique successor, right? So I think about this is a unique successor of, let's say, let's give a name to the array, let's say A of A at index I. Right? What about linked list? Similar. But linked list is going to be like a chain structure. So let's say we got the starting point. Let's say this is node, right? Let me draw a little bit more simply. It points to the next. This one points to the next, and then etc. All right. Let's say we have a node over here called n, right? Let's say this is m. So we can also say m here is the unique successor of n. More precisely, because n aliasing is equal to n dot next. All right, so these are the two instances of linear collection, okay? Array or linked list. What about nonlinear? You basically just relax that assumption. The successor may not be unique anymore. And that's something we're going to touch upon very deeply after reading week, which will be about trees. Each position has multiple successor, not unique anymore. So for example, what we're going to see, a particular kind of tree is called binary tree. So binary tree will look something like this. Okay. So you have some node over here to start with. And usually when we draw the tree, we draw it vertically. Okay? So you can imagine that there will be two references rather than just next reference. And one of them, for example, is going to be called left. And the other one is going to be called right. Each one of them is simply pointing to another node. Another node. So you can think about this one here and this one here. Both of them are just considered as the successors of this particular node. They are not unique, right? So that's not linear. And the number of nodes, the number of successors may not be just two. So I'm just drawing one example. The number of successors can be multiple, can be even a collection itself, right? That's something we'll get into more details when we talk about tree, okay? So for this part over here, you can think about we got multiple successors. Of, let's say this, just call it n. All right, so be clear about linear versus nonlinear. Okay, but now we talk about linear for linked list. Okay, and then we're going to talk about, let's see here, let's just go over the slides a bit. And we talk about there will be two references, one about the data objects, could be a string or can be anything, and also the next node. And we're going to see the Java code at some point as well today. And let's talk about this very important point here. The way you, in general, try to pinpoint or locate a node or position in a linked list is so-called relative as opposed to absolute. That's also something important to clarify. Okay, so let's now take a look. And we can even talk about how the running time will actually vary between the two. Okay, let's talk about here. Let's talk about array, first of all. So we talk about absolute indexing of arrays. Absolute in the sense that you can simply give some value indicating the position in the linear collection. Okay? So very easy example to see. For example, you can say 8 at index I. That's absolute. Or in general, it could be any integer expression that's in the brackets. So this will be some integer. And for those of you who already took 2031 or 2032, you know that in order to execute this, it's going to involve to calculate the address offset from A. And we know that A is the beginning of the array, right? Of the consecutive memory block. And calculating the address over here is going to be very, very cheap, very efficient. So that's why it's only a constant time operation. Big O of 1. So absolute indexing in the context of arrays is very cheap. That's something we said earlier, but doesn't hurt to put it here. So what about relative? Relative, I would say rather than indexing, because, well, we don't really have an index by default for a linked list. We can simulate it, but I'll talk about the simulation part. But just say relative positioning of linked list. Right, if I can write better. Positioning of linked list. Right here. All right, so we're talking about absolute as opposed to relative, right? So what's really relative? Again, let's draw some diagram here, okay? So we got, let's say here, oh, by the way, so sometimes we may also name the very first node in the chain as the head, which I'll speak a little bit more about, okay? We can say the head of the chain is a node over here. And that one there points to another one over here. And that one points to just another one. Let me just draw one more. That one points to another one. And then that one there has no next, so it would just be null. Okay? The relative part is really about the next reference. next, next, next. At the runtime, we simply don't know easily how many nodes are there in the singly linked list, for example. So that's why in order for us to get to a particular position over here, let's say we want to go to this particular node. The naive way to do it is to say we start with the head. And then say head.next to see if this is the one we are looking for. If this is not, we say next again. Is this the one we're looking for? If it's not, we got to go on. So the number of next references you may have to go may just correspond to the length of the chain in the worst case. So relative, in general, by using just the next references here, may not be that efficient, like array indexing. Okay. So here we can say the next over here, and the next over here, and also the next over here. So all these are the mechanism for relative. Because when you're at a particular node, you cannot really jump too many nodes ahead. You can only jump one node ahead by using the next. However, it is possible to somehow treat the linked list like an array. For example, why don't we have the following convention? Let's say the very first node is said to have index 0, index 1, index 2, index 3. Now, in order to kind of simulate this absolute indexing over here, is it efficient to really do so on the linked list? That's what you got to think about. For example, let's say if I have my list L, and I say, well, for the linked list, you don't really have this indexing notation. You don't. It's only reserved for array. So I may just have a method to say, I want to say L dot maybe get. I want to get to a particular index in the list. Let's say I. If you compare this operation over here and this operation here, which one will be more efficient, or the same, or something else, right? That's how you want to think about. Of course, to think about how efficient this is, you want to think about how large I could be. What's the worst case? I could be just maybe whatever the size is minus 1, right? So here, I here, you can think about the worst case, maybe just the last index, which will be the size of the chain minus 1. In that way, we don't really have a way. Well, of course, you could store maybe some special reference over here, but let's say we don't have that. Okay? In general, if you got some very large I, then you have no way around, but you got to start with the head and go all the way to that particular position. Then how many elements do you need? How many next references do you need before you can get there? It will correspond to how large I is. Because I, in the worst case, is very close to n, the size. So that's why the operation over here is going to be big O of n, linear. All right. Okay, so this one here is going to be big O of n in general. So we are talking about, let's say, just 0 here, 1 here, 2 here, and 3 here. So these are the absolute indexing that we can simulate on the linked list, but it's very inefficient. You have no way around. You have to use the next reference. All right, any question about these two? Absolute versus relative. Of course, on the linked list, you can do both, but it's just going to be very expensive to do relative indexing on the linked list. Okay. All right, so that's relative versus absolute. And then this question should be quite easy to answer. What's really so special about the last node in the chain? For example, if I look at the chain over here, what is so special about this particular node, which will be the last one in the chain, versus the rest in the chain? What's the difference here? Yeah, go ahead.
Points to null.
Points null, that's exactly right? So the property is the very last node here, you can see the next is simply just null. As opposed to, for example, all these, the next reference is not null. Actually, we did something very similar last time in the visual introduction. All right, so that's a very important property for you to keep in mind. Sometimes it could be the terminating condition for your loop whenever you want to iterate through the list. So for the last node, the next reference will just be equal to null, right? It's a very important property. And of course, whenever you want to change the last node, you got to change somehow the next reference for several nodes. That's something we'll see as well. Okay. All right, that slide is done. Good. Let's now talk about some interesting aspect about the list. Okay. Let's now, okay, let me just go back to the notes over here. The next point is about the chain may grow or shrink dynamically. So what do I really mean by that? Okay. So dynamically here is really the key word over here, dynamically. That means at a runtime, we may somehow choose to really either make the list larger or make the list smaller. And in many occasions, making such changes might be quite efficient on the linked list as opposed to being very expensive in the array. If you remember, we said inserting and removing from, inserting into and removing from the array, it will be very expensive. It's kind of like a linear operation. But in singly linked list, for many of them, it will just be a constant operation, as we'll see. So let's see some example here, some visual example. Okay, and I'm going to maybe draw in a way that will be also quite close to how you're going to implement it in Java. So that will also give you some idea. Maybe once you get to maybe assignments, or when we talk about some example in the lecture later. Okay, so what I will do is let's now go over different occasions, right? So there are 6 cases over here. Let's say I want to insert, let's say I got some chain of nodes just like that. I already got 3 of them. Sorry, 4 of them. 4 nodes already in the chain. What I want to do is I may say I want to insert maybe Toronto into the front of the chain. I may want to insert Vancouver somewhere in the middle. I may want to insert, let's say, Montreal to the end of the list, right? So these are the 3 occasions, and I'll get to the detail. And when you want to remove, let's say, I may just want to remove the very first node in the chain, or I want to remove somewhere in the middle, or I may want to remove just the last one from the chain, right? So these are the 6 very fundamental operations you may want to perform. We'll talk about quite most of them later in Java, and also do some tracing. But for now, let's think about what will be the steps that will be involved in doing these. Okay, let's now start with the first one. Okay, let's say I want to insert, let's say, Toronto to the beginning. All right. For the first one, let me do it from scratch with you. Okay. So step number 1, I got to create a node, right? So what I will do is I'm going to create a node like that. And the node for the data part, I don't really have any reference point. I just say Toronto, but you see what I mean. I'll just say Toronto here. And in the beginning, maybe the next reference is simply just null, right? Just create a node, number 1. And then let me call this particular node just T, which will be useful when I refer to it. Right, that's step number 1. And step number 2, because I want to insert this node as the new first node, eventually I also need to set it to be the head, which will be pointing to the very first node in the chain. Right? So I can do step number 2 to say for T.next, right now it's actually null. Rather than pointing to null, I will let T.next point to the current head. All right, I'll write it down. Okay, so step number 2, rather than pointing to null, I'll let it pointing to the current head. So this step number 2 is going to be T.next is assigned to the current head. And final step, now that I already got this guy here, followed by this, followed by that, so now the head should not be this second node anymore, right? So now I should also set the head to be T. All right? So step number 3. I'm going to say the head, rather than pointing to this node here, is now going to point to this node over here. That's step number 3. So step number 3, I'll put it here. That would be the head is assigned to just T. So these are the 3 steps that should be somehow performed sequentially to insert this particular new node with the data. All right? And you can already imagine how you can put it into Java, right? I already gave you almost half, almost there, the implementation, right? All right, so that's the first case. And then let me just highlight the steps over here, and I also have some question at the end for you. 1, 2, and 3. All right. Second case. Let's say I want to insert another node, let's say Vancouver. Let's say into the middle. All right. So when I say the middle, I'm being a little bit vague. We'll talk a little bit more precise detail later when we see the Java code. Let's say this. Let's say when I say the middle, I really meant, let's say I got N over here. Let's assume when you are programming this particular algorithm, you have some input parameter for the method N. That one points to some node in the chain. I'm telling you, I want to insert the new node right after N. So you're given this assumption, okay? So you can say the N here is assumed to be an input. So here I'm just doing a little bit more easily since we're just trying to get some intuition. In a slightly more complicated variant, we might say we want to insert into the middle, but maybe at a particular index. So rather than giving you a node reference to insert after, I might just give you some index number, in which case you have to write a little bit more complicated loop for that, right? That's for later, right? But for now, let's say the idea will be we want to insert Vancouver right after this N here. That'll be in the middle. So what should we do? Conceptually, let's jump ahead a little bit. How should a new diagram look like? I should really get a node here that's going to store Vancouver. And then somehow, this next is going to point to here. This node next is going to point to here. Right? Put it in the middle. That's what I want to achieve. Following that? How do we achieve that? Right? Let me write down the steps. Number 1, we got to create a node first, like before. So we're going to have, let's say, this here. And let's say that node here, I'm talking about Vancouver. And let's call this here V, right? We can also refer to it later. Eventually, we want to have the reference set up in such a way. But since you're going to implement it in a sequential algorithm, you got to watch out the order of the instructions. Right? Let me give you the correct one first. I'll give you some exercise to think about after all these 3. All right, so step number 1, you just create the new node. That's done already. All right, step number 2, I would like to say v.next should be set to n.next. Because after the insertion, the next node for this one here should be this one here. And this node here should not be the next node for this one here anymore. Right? That's how I insert in the middle. Okay? So what I will do is for step number 2, I want to achieve this one here. Guys, any suggestion? What should I write here to do the variable assignment? What should I write? You got all the variables here. So what should I write to do that arrow? Please help us out.
v.next equals n.next.
Yeah, as easy as that. Good. So v.next is assigned to n.next. Right? So we are saying that v.next, so to be more precise, in the very beginning, that should really be pointing to null. But I don't want it to point to null anymore, let's say. Okay? So step number 2 is going to make sure v.next is going to point to n.next. We're creating alias over here. Right? That's step number 2. And the final step should be, well, this node here. So now at the moment, the collection temporarily Okay, sorry, let me hold that thoughts. It might be a little bit too advanced for now. So what I want to do is, I don't really want this guy here, the next to be this node here. It should not be right. So the next node for this guy here should be to this one here, right? So I'm going to erase that, and then I'm just going to let it point to here. So that'll be step number 3. That one should be, and next should be assigned to V. So these are the 3 steps. 1, 2, and 3. We're good? All right. We're also learning, like an algorithm design, really, just using diagram. All right. What about the last one? The last one, let's say we want to insert Montreal to the end of the list. So the idea would be we want to, again, create a node, and then we'll let what used to be the last node, its next should point to this node. And what we used to call the tail, by the way, tail is more like an explicit reference for the very last node in the chain. We'll see that later. And that one there, we want to make sure tail points to this new last node instead. Right? That's what we're going to do. Only 2 steps. Step number 1, we can simply just create a node for Montreal. So we got Montreal over here. And then that's step number 1. And then that one there is going to point you now in the beginning. And then what about second step? Second step would be we want to make sure this one here no longer point to now, but it's actually going to point to right here. Right? So this one will be tail.next is assigned to, let's say this one here, when we first create it, is going to be n equals n. Right? Should be 3 steps rather than 2. We also need to make sure the tail, rather than pointing to here, is now going to point to this new node, the new last node, number 3. You can say the tail equals n. 1, 2, and 3. All right, I can put all the 3 operations in a single picture, so just to show to you, right? And exercise for you to think about, okay? For this particular exercise, right, you can see for each of the operation, the first step is always about creating the new node. That's okay. Now my question is, would it work if we simply swap the order of 2 and 3? So let's say I want to execute this one first, followed by this one. Okay, think about it. That should be rather easy for you to answer. So the best way for you to really convince yourself whether swapping step number 2 and 3 for each scenario would be to trace it visually. So that's really the technique you need in order to design algorithm on the linked list. All right. And also another thing to mention, in order to really understand linked list very well, you have to understand like a reference and manipulation over here. Redirecting the arrow, aliasing is a must. So for those of you who still don't feel comfortable about aliasing, maybe from 2030, reach out to me. We might need to catch up some basics, right? But that's very important. Okay. All right, let's now talk about removal. Okay. For removal, I'm going to do 2 of them, and the last one will be exercise for you. You can also think about the last one. Okay, the first one. Let's say we want to remove, let's say, LA. Let's say we want to remove this particular node from the chain. Let's say. How do we do that? Basically, that one there is just removing from the beginning. Well, sometimes people simply say remove first, right? You don't need to say the name of the node. That one there should be quite easy, but this one here, you may need some temporary variable to help you a bit, right? Because if you simply say, for example, if you simply say, I set this reference over here to be null, for example, then you lose it. Now, then once you set this one to be null, how can you know what the reference for this one would be in order to set a new head? All right, so that's something I can put also as an exercise for you. Okay, let's see the steps. Okay, step number 1, we don't need any new node. It's about removing, but we need a temporary reference. And when you design the algorithm for linked list, you can have as many temporary variables as needed. So for the first one, I'm going to have some temporary variable, just call it temp. Temp is just an alias for the head. So I'm going to put right here. All right, that's going to be useful. All right, that's the first step. And step number 2, I can say, I want to set a head, because I know this is going to be removed. Head should be set to over here. Agree? I'm going to write down this variable assignment. Head over here is going to be assigned to, this might be something that look very weird to some of you. Does it seem weird to you when I say head is assigned to head and next? If you say no, that's good. Good for you. All right. So the way to understand about this line is head over here, rather than pointing to the current one, is going to point to its current next. Head.next is currently this one here. So head, rather than pointing to here, is going to point to here. That's what it is saying. All right. So by doing that, head is now going to point to this guy here. And we are not done yet, because somehow we don't really want more than 2 references pointing to over here. Doesn't seem to be completely like a linear collection, right? So what we want to do is set this one to be null. Okay. And this one here, you can see we already lost the reference for head. So how do we know this node again? Well, we got temp, right? That's why we need a temporary variable in the beginning. So now for step number 3, we're just going to say temp dot next is assigned to null. So that one is going to remove this one. So this one will make sure this node that we want to discard has no reference to any other node. So at some point, it will be garbage collected by Java virtual machine. That's also important, because we don't really have to do any explicit memory management, but whenever if you can set the reference to be null so that the node becomes isolated, it'll be helpful. Okay. So we got 3 steps over here. We got number 1, number 2, number 3, right? And the step number 1 is crucial. Let's do a final one. And then the last one, I'll describe that briefly, and then that'll be exercise for you. The last one. Let's say we want to remove from the middle. That's also worth our attention, because that one there has different variants that you also got to watch out for. Okay. So for this one here, let's say I want to remove Atlanta from the middle. So basically, I want to remove this one here. And conceptually, pretty easy. I basically just have to make sure I set a pointer like this, and remove this pointer, and remove this pointer, conceptually or visually. But in reality, it's not as simple, right? So let's make the following assumption. Let's say for this algorithm here, you're given 2 inputs, let's say. You're given input number 1 and input number 2. Let's say you're given input number 1, output over here. Let's call that N. And then I got input number 2. I call that PREV, standing for previous. It turns out, in the context of singly linked list, where you only got next reference, if I want to remove this particular node, very likely, in order to reset the references, I would need to know what's the reference for its previous. But the problem is, I don't really have a previous reference back to it. I don't. That will be something called doubly linked list, which we'll get into. But for now, we're talking about singly linked list. And in order to really calculate, let's say given this particular node, how do I know what the previous is? If I didn't really give you this one here as an input, then you will have no way around but to start with the head, go all the way to the node where the next will be equal to n. That one there is more like a linear operation. Okay, that one is more like a conceptual sketch. But I will do that a little bit more precisely once we get to the method. But for now, you just got to remember, you're lucky that previous is given to you. It's cheaper. But most likely for your algorithm, you might be just given n, in which case you're told to remove n from the list. But in order to do it, you also need to calculate previous yourself. Okay, just remember that. All right. But let's say we are given the previous, so we don't need to worry about how to compute it. So we want to remove this node from here. Okay. So the idea would be we want to somehow set a reference like this and remove this. Okay. Let's see the steps that will be needed. All right. So step number 1. Okay. So step number 1, we can simply just do this. Rather than pointing to that n, which is going to be removed, let the next reference for the previous point to here. That's the first thing we want to do. All right. For that first step here, I'm just going to tell you what to do. So you can say previous, that's given, the next will be assigned to n the next. Question for you. Is this the only way to write it? Well, there might be an alternative way to write the same effective assignments because of aliasing. What are you thinking?
Can you write previous dot next equals tail?
Equals tail? I see what you mean. In this case, yes, tail is right here. I agree, but not in general. I like the idea. Yes, according to the diagram, you might say this guy here just tail. I'm thinking about something a little bit different. Yeah?
Maybe like previous dot next equals previous dot next dot next.
Exactly right. Thank you. All right. So what your fellow student said was also right. So this part over here, because of aliasing, alternatively, you can also say previous dot next dot next. That will also work because we know that n dot next is referring to this node. Previous dot next is also referring to the same object. Doesn't matter which one you use. All right. Very nice. All right. So that's the first step. And the second step, we just want to make sure this one here is gone. This reference here, right? That will be the second step. So the second step will be, I don't want that anymore. So I'm just going to remove this reference over here. So second will be just to say, and next will just be assigned to null. Oh, yeah, that's like that. Yeah, make sure that's removed. All right, so we got 2 steps over here. All right, let me highlight them, and then I'll tell you something you can think about as exercise. The final one is like this. Let's say I want to remove Boston from the end. I want to remove this guy here. We are basically facing a similar situation as removing this node over here. In order to remove this guy here, we need to basically conceptually the second last node, if I may, right? Second last node. This is the last node. That's the second last node. In order to remove the last node, I need to know where the second last node is. From there, I'm going to set the next to be null, and then also get rid of this reference here, right? Conceptually, that's easy. But the problem is, how do I know where the second last node is? Either you're given the reference, then you're lucky, that's cheap, or you got to compute it. All right? But for now, let's assume you are given that. All right, so now I'm just going to say, let's say we assume the following. So let's say we assume you actually got I would say SL, standing for second last. Let's say you're given that. So now can you somehow work out the steps for removing the last node based on the second last reference that's given to you? Right? Of course, you may want to use tail as well. All right, so exercise. So now this one here will be exercise. Okay, and you're given SL, which is the second last node. So the various scenario we are talking about over here is very valuable. Again, we are not really touching any code, even though we are working out some reference aliasing assignment. But this is really how you should really sketch the idea when you receive the assignments, or maybe receive the task in the actual programming task. So to really work out the correct algorithm on the linked list, very often you cannot just think in your head. You got to really visualize what's happening here. All right, we'll do more visualization as we go. All right, guys, any question? All right, I think that this will set some very solid ground when we talk about individual different methods when we get to coding. Right, this is really important. That's why we're spending a little bit more time on this. All right, so I think the next one will be to talk about the actual Java. Right, I still got about 20 minutes. I would suggest we'll take a very short break by taking attendance, and we'll resume. All right. Okay, I think we're good. All right, so let's now talk about the Java implementation for the linked list. So as far as the slides are concerned, I think we're done with basically all the introduction. We actually did way more than what's on the slide, so you should definitely review the stuff that we talk about. And the exercise I kind of put on the end of the slide here, just about counting the number of nodes currently in the list. You can think about it, but we're going to do that maybe not today, maybe next time. And also how you can find the reference to the tail. That's basically the next two methods we're going to talk about. But today, I'm going to focus on the Java implementation, the classes you have to write, and also some basic construction for the new objects. They are not that trivial, so that might be something we can focus on today. But these two exercises we'll get to from next time, Thursday. All right, so Java implementation. So you will need basically two classes. You will need the node class for each individual node. You will also need a top-level singly linked list class. So these are the two classes we're going to need. I'm going to show to you, and then we'll visualize how you can use them. So let's talk about individual node first. So for the node here, so that's a class. And you can see right here, corresponding to what we said earlier in the introduction, we got elements or data, and also we got a next. So that'll be the relative positioning mechanism, right? And one thing to note, you can see that the type over here, the node here, is corresponding to the class itself. Not surprising, that's how the linked list is actually, the chain of nodes is actually defined. And there is a formal name for this kind of mechanism, okay? It's something called recursive type. Recursive in the sense that in the same class, you simply use the class itself as the type. That's where the name recursive comes from. Like how you call the method by itself, right? It's called recursive method. So here we got something called recursive type. And recursive type is very common. All right, so we got that means each node we got elements, and also we got next. Let's now visualize right away. You can think about for each node you're going to create for the objects. So let's say it's a node. And for each one of them, we got two attributes. We got element, we got next. So I might just say E for elements and also N for next. So these will be the two references we had to set up. But for now, we can assuming that the element is simply of type string. But later on, once you receive the assignments, we're going to make this particular type over here for the data generic. I'll speak more about it, maybe once the assignment is released. But for now, the element here is going to be the reference to some string. And the node over here, maybe just to another node. Okay? So this will be the reference of some node. Of course, it's got to be the successor for this particular node, right? We talked about unique successor before the break. And then, of course, when you first create a node, you might also give some reference to it, right? That can be N, all right? That's about the node class, how you can use it. And we'll talk about the constructor later, very soon. So let's say when you want to first create a new node, you're going to pass the data and also the reference to the next node. We're going to see how you can construct a chain of nodes using the constructor here. We're going to see that in a moment. And you got get element returning just the data. Also, you can set the elements. You can get a next. Also, you can set a next. So these are the fundamental operations you will need to implement your algorithm. We got another class over here. This class is called singly linked list. Meaning that when you use the constructor over here, for example, I don't have it here. So that has a default constructor, which will just initialize everything to be null. Okay? But what attributes do we have? For now, let's assume we only got one attributes. That one there is just called a head. Just a head. Later on, we'll talk about how you can introduce maybe additional attributes to save some time. But let's not get there just yet, right? For now, assume we only got head attributes. What's going to happen is, at a runtime, you might say, I want to create a new singly linked list objects. Okay, let me just use purple here. You got a singly linked list. Let me call it L. Okay, list. That one there is pointing to an object of type singly linked list, SLL. And for now, we assume there's only one attribute, which is called the head. And the head is of type node. You can see the node here is really referring to the node right here, right? That's how the connection goes. At a runtime, you can expect that in the beginning, when you first create the singly linked list, it's going to point to null. But at some point very soon, you can say, I built a chain of connected nodes, like how we discussed earlier. And then I can simply say, now the head, L.head, is simply assigned to n. Once I've done that, it's going to say, now the head of the list is now going to be over here. That's how we usually do things, right? You got to build a chain of nodes and then set a head to be the beginning in the chain. All right? Any additional algorithm on the singly linked list is going to be defined in this particular class, singly linked list. We don't really define them in the node class. The node class is only for some basic operation for setting the node level references. Right? You can set a head, right, which we just did. Or you can get a size, get a tail. You can add first, get node at a particular index, which we talked briefly about. And also you can add at a particular index, like an insert at. Or you can remove last, and etc. So all the algorithm you might implement will be at this level, the singly linked list. All right, any questions just about the Java code itself? You'll receive something very similar as the skeleton that you can always take for granted for both the assignments and the programming test. Yeah, question?
Why don't we use the .next for the nodes? Like this .next or this .get element?
Are you more talking about, sorry, which method are you talking about? Get next?
The node. So like return element. Why don't we use like this .return element instead of?
You mean rather than saying n.next, so why do we say n.get next? Is that what you're saying? So here, okay, maybe I'm just guessing. Maybe you can see these two attributes are private. So for good engineering principle, software engineering principle, we have to make the attributes private and then define some public accessor for them. Okay, so that's why we got get next over here. Mm-hmm. Yeah. Maybe that's kind of somehow answer your question? Yeah. Okay, yeah, we'll follow up later. All right, let's now see some example code to build the list. The first one. There are two ways to build a list. Let's say what I want to do now is I want to build the following list, a chain of nodes. Let's not worry about singly linked list just yet. Let's focus on building the node, the chain of nodes. Once we build a chain of nodes, it can set a head to be the head of the list very easily. Okay? Let's say my goal is to have, I want to have Alan followed by Mark followed by Tom. This is my goal. All right, so this is one way to build it. All right. Somehow we have to do in the reverse order. We'll talk about it, but just let's follow through. Somehow, if you want to build a chain like Alan followed by Mark followed by Tom, you have to somehow create a node Tom followed by Mark followed by Alan. Somehow. But let's see how that can be done first. Let's just trace the code faithfully. Okay. So let's say we got Tom over here. And also we got Mark over here. And also we got Alan over here. Okay, let's trace these three lines one by one. The first one, we say we want to create a new node that's called Tom. So think about, we actually got Tom over here, and that one there is going to point to a new node. And as we know, every node has two attributes. We got the elements, and also we got the next. And then the element here is going to be the Tom, right? You can see that one is passed as the element here, right? I may not trace into that many details. You guys should know how to trace, right? It's like a basic OO code. All right, so that one there is pointing to, let's say, Tom. And then the next is going to be just null. First node, which will be placed at last, because our goal is to put Tom as a third one in the chain. Second line. This one is interesting. We're basically trying to do two things. We try to create a node pointed to by mark and set its next as part of the constructor. Because you can see here, we are referring to Tom right here. I'll give you a little bit more detail, but let's say here, we're going to say we create a new node called mark. And that one there is going to point to a new node right here. So the node, again, has the elements. Also, it has the next. The element here is simply just mark. And for this part over here, let's trace very quickly. Okay, you can see we pass simply Tom as a second argument. That means you're going to call the constructor over here, and the n here is going to be replaced by Tom. And then there will be some implicit this dot next equals, so n will be just Tom. And what's this? Since we are creating mark, so mark will be the this, right? So it boils down into mark. The next is assigned to Tom, right? That's something very important for you to make sure you're convinced, right? Kind of basic OO tracing from 2030. I'll do the first one, just in short. Just be sure you're okay with it. And that one there is going to set mark the next to here. So a single line over here is going to do creating the objects and set the next to be Tom right here, the arguments. Similarly, when we do the third line here, Alan, we'll do something very similar, right? That one there is going to create Alan pointing to right here. And then we're going to get the node. We got element, and also we got next. Element will be Alan. And then we're passing the argument for the next, for this new node, mark. So that means the next is now going to point to wherever mark is pointing to. Right? That's a setup. And let's look at aliasing right away. Right? If I try to look at this node over here, let's say this node here. How many ways are there for me to refer to this particular node? First of all, how many? At least one. I can say Tom, that would just refer to this node, but there are more than that. Another, yeah, just give me another one. Mark the next. Another one. Alan, the next, right? So these are the three possible ways, right? Let's write it down. Aliasing. So either you can say Tom, or you can say Mark, the next, or you can say Alan, the next, dot next. All right, like that. Question?
One more. If we know it's the tail, we can access it through.
Yeah, for sure. Yeah, if you know the tail. Yeah. Let's say we don't have tail in this context. Usually, that's a good question here. Usually, tail is an attribute in a singly linked list level, not at the node level. But now here, we only talk about node class, so there's no such attribute just yet. Okay, you will see that very clearly next time. Okay. All right, guys, any question? All right, that's good. I'll stop here and then starting from Thursday, we'll move a little bit faster to talk about different operations on the syncly linked list.